Black hole lab. As we've seen in previous labs, it's possible to predict the motion of an object if we know or can accurately model the forces acting on the object. In this lab, we're going to do the opposite challenge. We have good motion data for an object, which is our star, but we don't know what the net force is acting on the object. So we are going to attempt to find it. We do know the position of the black hole, although as mentioned, we don't know its mass. The position of the black hole is represented by the red dot below. We also know the mass of the star, the black hole position, and the time step. Our model. From the position points, we were able to collect the velocity, and with the velocity, we were able to get the momentum data. Once we had the momentum data, we could observe the change in momentum, and then we used the change in momentum to get the net force acting on the star. Now that we have the net force that exerted on the star, we can find the mass of the black hole using Newton's law of universal gravitation formula. It's written as the force of gravity equals a constant, which is g, times mass 1, which in this case is the star, times mass 2, divided by the radius squared. We can find the distance between the star and the black hole, which is the radius, so we have that, and then we rewrite the formula as mass 2, because that's the mass of the black hole, to equal the force of gravity times the radius squared, which is the distance between the star and the black hole, divided by g, which is the constant, times mass 1. And since we have the force of gravity, the distance between the two, g, which is the constant, and the mass of the star, we can then find the mass of the black hole. A couple things we assumed in our model were, first, we assumed that the net force in the system was due solely to the gravitational force of the black hole, and second, we assumed that our time steps are small enough such that we can approximate derivatives like the derivative of momentum, which is a calculus concept. The yellow arrow is the net force and is always pointing directly towards the black hole. This could be due to the result of the gravitational attraction between the black hole and the star. The blue and the black arrows are always perpendicular to each other. The black is the net force parallel and always points in the direction of the tangent to the curve. And the blue is the net force perpendicular, which always points in the direction of the center of the kissing circle. They are just the components of the net force. As you remember, every vector can be broken down into components. This lab means many things. First, the biggest thing I think it means is that it shows us that we can use this very simple knowledge of physics and calculus and be able to prove and figure out forces between, like our imaginary black hole and a star, which could be used to really understand and gather anything in our solar system and other solar systems. But to get to more specifically, but to get to specifically what the "what does it mean" question is the following. The things that are equivalent are the net forces and the instantaneous changes in momentum. The changes over a day versus the instantaneous changes are completely different, but the forces, the net force and the instantaneous change in momentum are the same. Given the synthetic data set that we have, we can assume that the uncertainties in the momentum are relatively small. So delta P over delta T is an okay approximation of the small change in the momentum over the small change in time. If, for example, the mass of the black hole was increased due to our Newton's law of gravitational forces formula, we would then realize that the force of gravity would be much greater because the mass of the black hole and the force of gravity vary directly. And all of our data that we would collect would be much different because then we would find a different mass for the black hole.
Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids. Math, science, history, unraveling the mystery that all started with a big bang.